You need to hear this before it gets buried under 100 clickbait headlines that get the physics wrong. Somewhere beneath the French-Swiss border, in a 27-kilometer tunnel where protons are smashed together at nearly the speed of light, something happened that made a room full of some of the most cautious, skeptical, evidence-obsessed people on the planet sit up and stop talking. Physicists do not panic easily. They spend entire careers trained to distrust their own excitement. And yet, in December of 2025, a result came out of the LHCb experiment at CERN that made several of them use words they almost never use in public: crack, tension, and, carefully, nervously, new physics. By the end of this video, you will understand exactly what they found, why it terrifies some of them and thrills others, and why the difference between those two reactions might be the most important thing in modern physics right now. Stick with me, because if you think you already know what new physics means, I promise you the reality is stranger, more careful, and more human than you expect. Let's start with who is actually telling you this. The result at the center of this story was published by the LHCb collaboration, one of 4 major detector experiments built around the Large Hadron Collider, and it was independently checked by a second experiment called CMS. William Barter, a physicist at the University of Edinburgh and one of the co-authors of the study, called it among the most significant results the LHC has produced in years. This isn't a fringe claim from an obscure blog. It's peer-reviewed work heading toward publication in Physical Review Letters, one of the most respected physics journals in the world, built on data collected from hundreds of billions of particle collisions. So when I tell you physicists are unsettled, I don't mean a handful of contrarians on social media. I mean researchers who have spent 50 years defending a theory so successful it has never once been definitively broken. Before we go further, quick guess. How many 5 sigma adjacent particle physics anomalies from the last 30 years do you think actually turned out to be real, new discoveries once the dust settled? Take a second, think of a number. I'll give you the honest answer later in this file, and I promise it's lower than most people assume, which is exactly why the reaction to this new result is so unusual. That theory is called the Standard Model, and you need to understand what it actually is before you can understand why this result matters. Imagine you had a single rulebook that could predict, with staggering precision, how every known particle in the universe behaves, how electrons orbit atoms, how quarks bind together to form protons, how the forces of nature push and pull on matter at the smallest scales we can measure. That rulebook is the Standard Model. It describes every known fundamental particle and 3 of the 4 fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. Only gravity sits outside its reach. For half a century, this framework has predicted the outcomes of experiments so accurately that physicists half joke it's almost suspicious. You fire particles into each other at nearly light speed, run the numbers through the Standard Model, and the model tells you, often to many decimal places, what should come out the other side. And for 50 years it has kept being right. Here's the problem. Physicists know it can't be the whole story. The Standard Model doesn't explain gravity. It doesn't explain dark matter, the invisible substance that appears to make up roughly a quarter of the universe. It doesn't explain dark energy, the mysterious force accelerating the universe's expansion. It doesn't explain why matter so vastly outnumbers antimatter when the early universe should have created equal amounts of both. Physicists have known for decades that somewhere, hiding in the data, there has to be a crack, some tiny deviation, some particle behaving just slightly wrong that would point the way toward a deeper theory. The trouble is, for 50 straight years, every single time they've gone looking for that crack, the Standard Model has closed ranks and proven itself right again. Now picture the Large Hadron Collider itself, this enormous machine built specifically to go hunting for that crack. Protons are accelerated in opposite directions around the ring, steered by giant superconducting magnets, and smashed together at close to the speed of light. When they collide, the energy of the impact briefly converts into new particles, in accordance with Einstein's famous equivalence between mass and energy. And those particles decay again almost instantly into showers of other particles that the detectors capture and reconstruct. It is, in effect, the most expensive and most sensitive microscope ever built for looking at the fundamental structure of reality. And for over a decade, this microscope kept finding exactly what the Standard Model predicted it would find. Nothing out of the ordinary. Just theory, confirmed again and again. To actually catch a B meson in the act of decaying, you need equipment with an almost absurd level of precision. B mesons don't sit still and wait to be studied. They form for a fraction of a second after a collision, and then immediately fall apart into a cascade of lighter particles, spraying outward in specific directions and at specific energies. The LHCb detector is built, layer by layer, specifically to track that spray. Silicon sensors thinner than a human hair, positioned just millimeters from the collision point. Magnets that bend the paths of charged particles so their momentum can be calculated from the curve, and calorimeters that measure how much energy each fragment carries as it slams into the detector material. Every single one of those measurements has to be combined, reconstructed, and cross-checked against theoretical predictions for hundreds of billions of collisions before a pattern like this one even becomes visible. This isn't a single dramatic snapshot, it's a mountain of statistics, built one collision at a time over years. Until now, maybe. Let's rewind for a second, because this moment didn't come out of nowhere. It's the latest chapter in a story that's been building since 2015, and if you don't know the earlier chapters, the ending won't make sense. Back in 2015, LHCb researchers noticed something odd in the decay of a particle called a B meson, specifically in what's known as a penguin decay, an oddly named but real technical term for a process where a particle transforms through an intermediate, unstable state before decaying into lighter particles. The angles at which the resulting particles flew apart didn't quite match what the standard model predicted. It was subtle, it wasn't dramatic, but it was persistent, and over the following years, as more data came in, the discrepancy didn't go away, it grew. Then other anomalies joined the party, and this is where you should pay close attention, because it's also where the story gets a lesson in humility. In the early 2020s, physicists were excited about a separate anomaly, a strange difference in how B mesons decayed into electrons versus muons, two particles that, according to the standard model, should behave almost identically except for their mass. If that anomaly held up, it would have been a direct violation of one of the model's foundational assumptions. Excitement built for years, and then, in 2022, with more precise data, the anomaly evaporated. It simply wasn't there anymore. In 2024, physicists at the LHC also quashed hopes tied to another apparent anomaly, first spotted by the Collider detector at Fermilab 2 years earlier, involving the mass of a particle called the W boson. And in 2023, revised theoretical predictions suggested that the long-debated muon G-2 anomaly, a strange wobble in how muons behave inside a magnetic field, which had tantalized physicists for over a decade, might not be a real discrepancy at all, once the underlying calculations were redone more carefully. I'm telling you all of this on purpose. You need to sit with it for a second. Physics has a graveyard of almost discoveries. Signals that looked electrifying, generated hundreds of excited research papers, and then quietly dissolved once more data arrived. If you only remember one thing from the first half of this video, remember this. Extraordinary claims in particle physics have a habit of not surviving contact with more data. And the physicists at the center of this new result know that history better than anyone. That's exactly why their reaction matters so much. Because this time, the B meson penguin decay anomaly didn't dissolve. It grew. Here's the actual result as precisely as I can give it to you without a physics degree standing between us. Using a dataset built from roughly 650 billion B meson decays recorded between 2011 and 2018, and cross-checked against newer data since LHCb has now recorded 3 times as many B mesons since then. Researchers measured a specific rare decay pathway and found that the particles didn't behave quite the way the standard model says they should. The mismatch, when you run the statistics, comes out to a significance of roughly 3.9 standard deviations, sometimes called sigma. In plain terms, that means there is only about a 1 in 16,000 chance that this result is simply a random statistical fluke, assuming the standard model is correct. Now here's why that number is both thrilling and frustrating at the same time, and this is the part where you get to test your own instincts. Before I tell you what the gold standard threshold is in particle physics, take a guess. If a 1 in 16,000 chance of a fluke sounds convincing to you, you're not wrong to be intrigued, but you're about to learn why physicists demand something much stricter before they'll use the word discovery. The answer is 5 sigma. 5 standard deviations corresponds to roughly a 1-in-1.7 million chance of a random fluctuation producing the result you're seeing. That is the line physicists will not cross before declaring something a confirmed discovery, and it exists precisely because of that graveyard of vanished anomalies I mentioned a minute ago. At 3.9 sigma, this new B meson result sits tantalizingly close to that 5 sigma bar, but it is not there yet. This is the honest, unglamorous truth sitting underneath every panicked headline you might see about this story. Physicists are not claiming they've broken the standard model. They're claiming they found something that refuses, so far, to go away, and that refusal is what's making them nervous. So why does this particular anomaly feel different from all the ones that quietly disappeared? 2 reasons, and both matter. The first is independent confirmation. A second, completely separate detector at the LHC, called CMS, measured the same decay process using its own equipment, its own calibration, and its own analysis team, deliberately isolated from LHCb's methodology to avoid bias. CMS's measurement is less statistically precise than LHCb's, but critically, it points in the same direction. When 2 independently built machines, run by 2 independently working teams, start agreeing with each other about an anomaly the standard model can't explain, that's a very different situation than a single experiment reporting an isolated fluke. The second reason is theoretical. This isn't a case of experimentalists finding a weird bump in the data with no explanation on offer. There's an existing theoretical framework involving processes physicists have nicknamed charming penguins. Yes, that's a real term used in published physics papers. And yes, it's exactly as delightful as it sounds. That already predicted deviations could show up in exactly this kind of decay if there's undiscovered physics at play. When a measured anomaly lines up with a theoretical mechanism that was proposed independently, rather than being invented after the fact to explain the data, that's a stronger sign that something real might be going on. Physicists have a healthy suspicion of explanations invented after the fact. This isn't that. So what would actually be causing this, if it turns out to be real? This is the part most coverage of this story skips entirely, and it's the part I find genuinely fascinating. The leading candidates aren't vague hand-waving about unknown forces. They're specific, named, mathematically defined possibilities that theorists have been developing for years, mostly in relative obscurity, waiting for exactly this kind of experimental nudge. One candidate is a hypothetical particle called a leptoquark, a theoretical object that would be able to transform quarks directly into leptons, something the standard model doesn't allow at all. Another candidate is a heavier, undiscovered cousin of a known force-carrying particle, sometimes nicknamed a Z-prime boson, which would introduce an entirely new force acting specifically on certain kinds of particles and largely ignoring others. Neither of these has ever been directly detected. Both have been proposed on paper, specifically because they would produce exactly the kind of deviation LHCb and CMS are now reporting. If this anomaly survives, one of these frameworks, or something closely related to them, stops being a hypothetical footnote in a theory paper, and starts being the leading explanation for how the universe actually works at its smallest scales. Let's pause here, because this is where I want to bring in the myth that's floating around every headline about this story, and set the record straight. The myth says, CERN has found proof of new physics, the standard model is broken, and everything we thought we knew about the universe is about to be rewritten. That is not what happened, and if any video, article, or influencer tells you otherwise, they are selling you something more exciting than the truth. The reality is more careful, and honestly, more interesting once you understand it. Physicists have found a persistent, statistically significant, independently corroborated tension between what a specific rare particle decay does and what 50 years of theory says it should do. That tension is currently sitting at 3.9 sigma, 1 sigma short of what they'd need to call it a confirmed discovery, and it needs more data before anyone can responsibly say the standard model has actually cracked. That's the reality check. Hold on to it, because it's going to matter again in a minute. Now, why should a number on a chart make anyone afraid? This is where the human cost of this story comes in, and it's easy to miss if you only look at the statistics. Consider what it actually means to be a physicist working on this problem. Many of the researchers involved have spent their entire careers, decades of their working lives, inside a framework that has never once been proven wrong at a fundamental level. They built their expertise, their reputations, their entire mental model of reality on the assumption that the standard model, while incomplete, is correct within its domain. If this anomaly holds up under more data, if it eventually crosses that 5 sigma threshold, it wouldn't just add a footnote to a textbook. It would mean there is a new, undiscovered particle or force out there, something with mass and behavior nobody has directly detected yet, quietly influencing how B-mesons decay. It would open the door to fields of physics research that don't currently exist. Careers would be built and unbuilt around it. Entire departments would need to rethink what questions are worth asking next. That is genuinely thrilling if you're a theoretical physicist who has spent years developing models that predict exactly this kind of deviation. Models that have been mostly ignored because there was no experimental evidence to support them. Imagine spending a decade developing a theory that almost nobody outside your small research group takes seriously, and then watching an experiment slowly, cautiously start to agree with you. That's not panic, that's vindication, arriving in incredibly small, statistically rigorous increments. Think about what that actually feels like day to day. You publish a paper proposing a leptoquark model in, say, 2016. A handful of people cite it. Most of the field moves on without a second glance. You keep refining the math anyway because you believe in it, even while your funding applications get harder to justify and your colleagues gently suggest you might want a backup research direction. And then, a decade later, an experiment you had no involvement in reports a deviation that lines up almost exactly with what your model predicted. That's not a headline. Nobody writes an article about the theorist whose decade-old paper quietly turned out to be prophetic. But inside physics departments, that kind of moment is enormous, and it's exactly the kind of quiet, unglamorous validation that keeps entire subfields of theoretical research alive during the long years when nobody outside the field is paying attention. But it's also terrifying, for exactly the same reason, if you're one of the physicists who has built your career on the standard model working exactly as written. 50 years of theoretical consistency is not a small thing to have hanging in the balance. And there's a deeper, quieter fear running underneath all of this, one that doesn't get talked about enough. The fear of being wrong in public, on a global stage, after everyone has already gotten excited. Nobody in this field has forgotten the 750 gigaelectronvolt diphoton anomaly from 2015 and 2016, when both ATLAS and CMS detected an excess of paired photons that reached 3 to 4 sigma of significance. It triggered roughly 500 theoretical papers speculating about what new particle might be causing it. And then, when more data came in during 2016, it simply vanished. 500 papers built on a signal that turned out to be statistical noise. Nobody wants to be the physicist who called a discovery that then dissolved on live television, so to speak, in front of the entire scientific community. This has happened before, more than once. Back in 1996, the Large Hadron Collider at CERN, the LHC's predecessor, saw an excess of events that climbed to nearly 4 sigma and looked eerily like it might be an early sign of the Higgs boson, years before the Higgs was actually confirmed. That signal disappeared as more data came in. And in 1998, physicists at Fermilab's Tevatron observed a bizarre anomaly nicknamed the superjets, reaching a startling 6 sigma significance, higher than the gold standard for discovery. And it, too, eventually faded from the record as more careful analysis was applied. Even 6 sigma results have vanished. That's how seriously you have to take the possibility that this new B-meson anomaly could still turn out to be nothing. So here's the honest tension every physicist working on this result is holding in their heads simultaneously, and it's worth sitting with for a moment, because it's rare that science lets you see this kind of intellectual honesty up close. Part of them wants this to be real, badly, because it would be the biggest breakthrough in particle physics since the discovery of the Higgs boson in 2012. Arguably the biggest since the Standard Model itself was assembled in the 1970s. And part of them is bracing, quietly, professionally, for the possibility that in a year or two, with triple the data, this crack seals itself shut just like every anomaly before it. That dual state, hope and dread occupying the same sentence, is, I think, one of the most human things about modern science, and it rarely makes it into the headlines that just scream, "Physics is broken." So what happens next? This is the bridge to where we actually stand today, in 2026, and it's less dramatic than a movie ending, but it's the truth. LHCb has already recorded roughly 3 times as much B-meson data as was used in this analysis, and that data is currently being processed. Further upgrades to the LHC are planned through the 2030s, which are expected to eventually deliver a dataset around 15 times larger than what physicists are working with today. Each new batch of data either tightens the statistical significance of this anomaly, pushing it closer to that 5 sigma threshold, or it does what so many anomalies before it have done, and gradually washes the signal back down into statistical noise. The LHC itself is also scheduled for a major hardware upgrade known as the High Luminosity LHC, designed specifically to dramatically increase the rate of collisions the machine can produce and record, which is part of why physicists expect that 15 times larger dataset to eventually become available. None of this happens quickly. Particle physics does not move at the speed of a headline. It moves at the speed of magnets cooling to nearly absolute zero, of detectors being recalibrated collision by collision, of statistical models being checked and rechecked by rival teams specifically trying to find flaws in each other's work. Nobody currently knows which of those two outcomes is coming. Not William Barter, not the CMS team, not the theorists behind the charming penguin models. Genuinely, nobody knows yet, and if anyone tells you with total confidence that they do, be skeptical of that confidence, no matter how exciting it sounds. That uncertainty, by the way, is not a weakness of the scientific process, it's the entire point of it. A result this significant, this potentially field-changing, should make careful people nervous before it makes them celebratory. That nervousness is the immune system of good science, and it's worth remembering the next time you see a headline claiming physics has been broken by a single press release. Real breakthroughs in physics don't arrive as a single dramatic announcement. They arrive slowly, painfully, through years of data collection, cross-checking, independent replication, and a whole lot of physicists refusing to get too excited until the numbers force them to. Before we close this file, I want to ask you something, because I'm genuinely curious what you think. If you had to bet right now, and I mean actually commit to an answer, not just sit on the fence, do you think this anomaly survives the next round of data? Or do you think it joins the graveyard alongside the diphoton excess, the electron-muon discrepancy, and the muon G2 wobble? Drop your answer in the comments before you finish watching, and then tell me why. I read every single one of these, and honestly, some of the most interesting theories I've come across for this channel have come directly from disagreements in the comment section. Viewers pointing out papers I hadn't seen yet, or pushing back hard enough on a claim that I went back and rechecked the primary sources myself. If you think I've gotten something wrong here, or if you think I'm being too cautious about a genuinely huge discovery, say so. That disagreement is exactly what keeps this channel honest. I also want to be straightforward with you about something, because I think you deserve that. Building an episode like this takes real time, digging through peer-reviewed papers, cross-referencing statistical claims across multiple outlets, making sure every number I've given you actually traces back to the original research rather than a diluted second-hand summary of it. If this channel has ever taught you something that genuinely changed how you see the world, and you're in a position to do so, a super thanks on this video goes directly toward the research time that makes videos like this possible. No pressure at all if that's not something you can do right now. The video exists either way, and I'm glad you're here watching it regardless. Here's where I want to leave you, because this story isn't finished, and I don't want to pretend that it is. There is one detail in this entire saga that I have deliberately not explained yet, and it's the detail that might end up mattering more than the B-meson anomaly itself. Remember the muon G-2 result I mentioned earlier, the strange wobble in how muons behave inside a magnetic field, the one that seemed to evaporate in 2023 once theoretical predictions were revised. That story isn't actually over. There's a brand new experiment called MU-on-E currently collecting data at CERN using an entirely different method than the one that produced the original muon anomaly. And there's also a separate, independently built experiment in Japan called JPARC using yet another completely different technique, expected to begin producing results around 2028. Two independent experiments using two different methods, both built specifically to settle a question that the physics community currently cannot agree on. If those two experiments end up disagreeing with each other, the way LHCb and the original muon measurements once did, we could be looking at not one, but two simultaneous cracks in the standard model, arriving within a few years of each other. That is not a hypothetical for some distant future. That is a real, funded, currently running set of experiments, and the first meaningful results could start arriving before this decade is out. And remember that guess I asked you to make earlier about how many 5 sigma adjacent anomalies in the last 30 years turned out to be genuine, lasting discoveries. Here's the honest tally, as best as the historical record allows. Across the diphoton excess, the LEP Higgs-like signal, the tevatron superjets, the electron-muon B-meson discrepancy, and the original muon T2 wobble, the survival rate is close to 0. Every single one of those either vanished outright or got explained away by revised theory. The only comparably dramatic result from the last several decades that did survive, that did get confirmed at 5 sigma and beyond, was the Higgs boson itself in 2012, and even that took years of accumulating data before physicists were willing to say the word discovery out loud. That's the actual base rate you're working with. It's not 0, but it's brutally close to it, and that history is precisely why this new B-meson result, sitting at 3.9 sigma with independent cross-confirmation from 2 separate detectors, is being treated so carefully by the people closest to it. So here's the unresolved question I'm leaving you with, the one this file stays open on. If the muon anomaly and the B-meson anomaly both turn out to be real at the same time, independently pointing toward physics beyond the standard model, what single new theory could possibly explain both of them at once? And are physicists already quietly working on one? Here's a hint at why that question matters so much more than it first appears. A leptoquark, the kind of theoretical particle I mentioned earlier, wouldn't just explain a strange B-meson decay in isolation. Some versions of leptoquark theory are specifically built to connect quark behavior and lepton behavior through the same underlying mechanism. Which means, if the math holds up, a single new particle family could potentially explain both the B-meson tension and a muon anomaly at once, instead of requiring 2 separate, unrelated new discoveries. That would be an extraordinary result. It would mean 2 seemingly unrelated cracks in 50 years of theory turned out to be the same crack, viewed from 2 different angles. Physicists chase that kind of unifying explanation precisely because nature has a track record of rewarding it. Electricity and magnetism turned out to be the same force, viewed differently. So did the weak nuclear force and electromagnetism, at high enough energies. If this pattern holds again, the story we're watching unfold right now may eventually be remembered as the moment 2 separate threads of a 50-year mystery turned out to be the same thread. I have a specific answer to that question, and it involves a class of theoretical particles that most people have never heard of. But that's a story for the next file. For now, you know more about what's actually happening at CERN than 99% of the headlines currently circulating about it. And that's exactly the reason this channel exists. I'll see you in the next one.